Okay. Uh, so I think now we are ready. Uh, Hi everyone. My name is Rohit. Wait. Yeah. Yeah. Hi everyone. My name is Rohit Kumar Singh. I'll be the teaching assistant for this course, Nuclear and Particle Physics, which is being taught by Dr. Paulos from IIT Guwahati. So I am a PhD student at IIT Madras, and we will have this live session every Saturday at the same time, 4 to 6 p.m. So I hope that all of you will join all of the session, and we will have a nice interaction. So in this live session, you can ask your doubts and whatever problem that you have faced in the lectures of NPTEL. And also we will have a problem solving session where I'll solve some example problems uh, for the given week, and which will help you to solve the assignments over the NPTEL uh, course. So yeah, so that is the plan. So do you have any question or anything that you want to ask? Hi, Jyotsika, yeah, please go on. Hello?
Yeah, hello. Am I audible?
Yeah.
Yeah, actually, I had a doubt regarding assignment one given in the course. It
Okay.
is that in some questions, it
Hmm.
is not said how much decimal place to estimate. So, should we take one decimal place or like two or three? Better if you
So,
make it clear.
so what happens is, for the answer we set a range. Okay, we set a range from which if your answer is correct, like even if you give the answer up to like 1 2 decimal places, and if your answer lies in the range that we set, then your answer will be marked as correct. So I think even 1 decimal place is also fine, as long as but it depends, like uh, what type of what type of answer that is. So I think 2 decimal place will be a safe option. Okay.
Thanks.
So we set a range, so there's no problem of having a wrong answer if you give only 2 decimal places answer. So because the range is there, so don't worry. Yeah.
And I had a question from the theory.
Okay.
It is, can you explain how we get the pairing term in the semi-empirical mass relation?
uh, Pairing term in the semi-empirical mass binding energy equation, right?
Yeah, yeah, yeah.
Okay. So is this from the week one lectures or week two lectures?
It's from the week one lecture regarding the nuclear properties, lecture two.
Okay. Yeah. So basically, the pairing term it comes from the you know uh, basically the so let me see. I mean, so the last term of the equation, right? The delta one, right?
Yeah, that the delta term. Yes.
Yeah, the delta one. Yeah, it comes from the because these neutrons and protons inside the nucleus, they are fermions, right?
Yeah.
So, and the fermions are, I mean, they have either spin half or spin minus half. So, that pairing is, leads to I mean, that kind of pairing of two fermions leads to that term, as far as I remember. But yeah, I'll have to check. I am also not very sure about that. Okay, I'll get to this later. Okay.
Okay, so sure.
Okay. So okay, have some, let's solve some problems. Okay, and let's so basically for today I have kept some basic uh, problems which will refresh the memory about various things in quantum mechanics and the basic concepts of uh, nuclear physics. So, and through those going through those problems, we'll learn some concepts, okay, which will help you in the later part of the course. So so let's start with that, and then if you have any doubt you can ask. Okay. Okay, so let's do that. So this is the first problem. So can you all are you able to read the question clearly, or is it too small? The font is too small.
It's visible, sir.
Okay, thank you. Okay, so starting with a very basic uh, problem. So yeah, so the energy required to knock out the electron from hydrogen atom in the ground state of mm, wait, what is happening? Okay, yeah, in the ground state of hydrogen atom. So all of you must know what this energy is, right? So it's anyone of you can answer. How much energy is required to knock out an electron from hydrogen atom? Ground state.
13.6.
Yeah, right. So yeah, this is a very simple one. Okay, so let's. Do you have anyone has any doubt here? Yeah. So once. So just I wanted to know. So all of you are in your masters, or some of you are in uh, bachelors of physics. Anyone from anyone doing bachelor of science, or all of you are
I am in bachelor's.
okay? Final year, or okay? Two are, I think, two people. Okay. So, but yeah, these things you must have learned, right, in the first year of your bachelor's, or I think this one is from also higher secondary. They also teach these things. So okay, So yeah, if you have any problem understanding anything, just let me know. Okay, I'll assume that you all are familiar with these things. So, okay, next up, we have a problem on quantum mechanics. So here we are given two energy eigenstates. Eigenstates of a quantum system, psi one and psi two. Uh, so once again, all of you had one course on quantum mechanics, right? Or is there anyone who has no idea of quantum mechanics at all? Okay, so everyone knows quantum mechanics. Okay, that's great. So yeah, so energy eigenstates of a quantum mechanics are given psi 1 and psi 2. Okay, and the energy eigenvalues corresponding to these states is also given E1 and E2. Okay, and E1 is greater than E2. Okay, so at t equal to 0, so psi t equal to 0, this is the state of the system. Okay, and the question is, what is the state of the system at a later time t? So at some arbitrary time t, oh, sorry. So anyone, so how to find that? What is the recipe? So what does it mean that this eigenstate has eigenvalues even? So this basically means that if you operate with a Hamiltonian on psi 1, it will give even. Sorry, right? And the same is true for the psi 2. No, the whole system is a linear combination of psi 1 and psi 2 at time equal to 0. So how do we find how the system evolves in time?
We just multiply the psi with e to the power minus I in t.
Yeah, yeah. I mean uh, that is the answer. But how? Why do we multiply it? What is the concept behind it? What is the recipe?
It's because the psi of the particle can be divided individually into the space part and the time part.
Mm-hmm.
So we are given with psi 1 and psi 2, which are two different space parts for psi in a given combination.
No, I mean, so this I have not written anywhere that the psi 2 is a function of x or anything. That is not the case. Okay.
We can simply solve the Schrodinger equation, the time-dependent Schrodinger equation.
Yeah. Schrodinger equation, right? The very basic of quantum mechanics. Just you have to say that Schrodinger equation, which dictates the evolution of any quantum state. Okay, so that's what you do, and that amounts to basically just multiplying, psi1 with this term, and this energy is the eigenvalue of the this eigen state. Okay, so this is the correct answer. So yeah, just remember where these things come from. Okay, anyone has any doubt here? Okay, if not, let's move to the next problem. So we have two electrons with angular momenta 1. Okay, so basically L1 and L2 both are 1.
Sorry, but in the second question, I had a doubt.
Yeah.
So, shouldn't when solving the Schrodinger equation, shouldn't it be like the constant should be IE1 upon H bar? Like
IE1
E to the like I didn't understand that thing, that shouldn't it be I minus IE1 upon H bar T if we solve the Schrodinger equation?
You mean this?
Yes.
So what we do is we basically sometimes we take H bar to be 1, but yeah, that should be the case here, or I think this should be the case. We assume H bar equal to 1, but no, wait, no. Yeah, I'll have to check whether we assume H bar equal to 1, or it doesn't come at all in this form.
Okay.
Yeah.
Thanks.
Okay. Yeah, good question. I'll have to check. Thank you. Okay, so yeah, then the next problem. So here we have two electrons with their angular momentum both equal to 1. So what could be the possible total angular momentum state of the system? So anyone can you guess the answers? So it could be multiple answer. So if L1 and L2 both equal to 1, then what could be the total angular momentum of the state of the system? So can we say that it's naively L1 equal to L1 plus L2, which will be just 2?
Okay.
L1 equal to L1 plus L2 plus L2 plus L1 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 plus L2 Is this true? Or are we missing anything?
So can the answer be D? 3/2.
D. How it could be D?
Total could be S minus 1 to S plus L, S minus L to S plus L,
What? S minus L?
to S plus L. The net I.
No,
I
no, no,
mean,
no. I'm just asking angular momentum, not the spin. I mean, just the not the spin angular momentum, just the azimuthal angular momentum. So yeah, this is not the I mean, this is obviously incorrect. It's simple, right? So, if, we cannot just add like this because these are added vectorially, right? If you remember, so it goes from L1 minus L2 mod of L1 minus L2 to L1 plus L2, right? Uh-huh. So what this will give us? So 0 and then 1 and 2, right? So all these are correct. Okay. Anyone has any doubt here? So just remember these are added up vectorially. So you cannot just add them like a scalar number. Okay, so yeah, these are just basic things to, sort of refresh your memory. Okay, so the next question is what is the frequency of light emitted from hydrogen atom in the first excited state when it comes down to the ground state? Okay, so just now there was a problem in which I asked the ionization energy of hydrogen atom. Now here we have a problem that from n equal to 2, uh, which is the first excited state, we have a transition to n equal to 1, okay, which is the ground state. And we are asked what will the frequency of light emitted. So we know that when a electron does transition from excited state to a ground state, then it emits a photon. So we want to know the frequency of that light, a photon. Okay, so the formula for the energy which will be,
Should it be D? Like, should it be option D?
B.
D.
D. Yeah, I mean, let's do a calculation maybe. So the energy will be uh, so energy emitted, it will be so in I think I don't know which one goes here and which one goes there, but let's do the calculation. So this is here 4 because n equal to n2 equal to 2, so this will give you 13.6 into 3 by 4, and energy is just h mu, so and so frequency will be just this divided by Planck constant, which is 4.1357 into 10 to the power minus 15, right? So yeah, because this into this will be 0.82, and then 0.82 into 3, no, this these okay, yeah, you are right, it will be around 2.47. Sorry, I'm not able to write properly. Yeah, you can work out this, but yeah, I think this one will be the correct answer. Okay, these are simple questions, so let's move quickly. Okay, here's one question on magnetic field. So magnetic field at distance r from a long straight wire. So long means you can assume it infinite. Uh, so what is the current for a what is the magnetic field if current I is flowing inside the wire in a long straight wire? Anyone of you remember?
I think it is option B as
B.
well.
Yeah, but what is the expression? It's something like mu naught I by
I
2
2
pi r, right?
wires.
Yeah, so this is the correct answer. Yeah, this is little interesting because the magnetic field due to a point charge, it goes like 1 by r square, right? But when you take a wire, uh, I mean point charge moving, uh, so it goes like 1 by r square, but when you take a wire, it gives you 1 by r, so this is interesting. Okay, no, one question from basic particle physics. So, which of the following set correspond to fundamental particles alone? So, fundamental particle here means that which you cannot subdivide or further uh, divide it into constituents. So, which is the correct option? Anyone has any
Your
idea?
option A?
Which
Yes, sir.
option? Option A. Which who I mean, those who are in favor of option A, please raise your hand. Okay. So I think two people option A. Then B. Anyone for B? No. Anyone for C? Anyone for D? Okay. I think we have two for D. So yeah. So the correct answer is D, right? Because in A you have quark, electron, and then you have meson. So meson is not a fundamental particle. It is made up of a quark and antiquark pair, right? And then proton we know is made up of two quark and I mean three quarks basically. And then neutron is also made of three quarks. Here also proton is there. So electron, photon, and neutrino, these all are fundamental particles. They have no further constituents. So this is the correct answer. Okay. Hi Sardai, do you have any question or you are raising hand for the call? Okay. Anyone? Is everything clear up until now? Okay. So then next question. So here is one decay process. So neutron going to proton plus electron and then antineutrino. So is this process possible or does it violate any rule? And if it violates, then which one of these rules does it violate? Can anyone guess? Hi. So does it violate the strangeness conservation? I guess no, because none of these have a strangeness. So a strangeness is a quantum number assigned to a strange quark. I don't know if you are familiar with it, but I mean, just take my word for it. So here neutron and proton does not contain a strange quark, it's just up and down quark, so no strangeness here. And then baryon number, so baryon number is assigned to basically baryons. So here neutron and proton are baryons, and both have baryon number 1, so baryon number is conserved. Okay, then lepton number, let's check lepton number. So lepton number is number assigned to leptons, which is electron, muon, tau, and neutrino. So here we have two leptons, electron and neutrino. So electron has lepton number 1, and then neutrino has lepton number -1, so these two get cancelled, so basically you have 0 on both sides. So lepton number is also conserved, so this is also not the correct answer. So I mean, obviously then C should be the correct answer, but does anyone know what is this isospin mean? And what is the isospin for these particles? No one? 0? 0 for which neutron, or okay, so I mean, roughly isospin is similar to spin, like quantum mechanical spin, but for uh, strong force. So for the particles which interact through strong force. Okay, so it's a very old concept. So it's sort of like a relic which has come along. I mean, no one uses right now isospin because now we know there are quarks and the flavor of quarks are there. So isospin is not needed right now, but it is an old concept. So still, I mean, we can check. So isospin. We can check any reaction. Uh, I mean, it's still valid that isospin should be conserved. So for neutron, yeah. So like I said, so neutron and proton both behave similarly in a strong force. Okay. So to differentiate between them, people introduce this isospin. So neutron has just isospin minus half, and then proton has the isospin plus half. Okay, and proton neutron are sort of a isospin doublet, like you have the spin doublet in the quantum mechanics. Okay. Similarly, pion have a spin triplet minus pi 0, pi plus, like this. Okay. So yeah, so then as you can see here, isospin of neutron is minus half, and then proton has half, and then others are 0. So isospin is not conserved. So that's why this decay violates the third component of isospin. It's called I3. So sort of like in spin you have the z component of spin, so here you have I3. Okay, anyone has any doubt? Feel free to ask anything. Okay, just don't be hesitant. I mean, I also don't know many things because my area of research is very different, and I have studied these things in my master's. So I'm also kind of remembering things. So yeah, we can have a discussion, and I can reply to your questions in the next session maybe. But yeah, don't be hesitant to ask anything. Okay. Okay, let's go to the next question. So this is just to remind you that the what is the ground state of hydrogen atom, and given A naught is the Bohr radius. So anyone remember which one is the correct option? Anyone? Just pick a random. Maybe you could be lucky. No idea. Okay, I'll just tell you. So the correct answer is this one. So you have the exponential falling as minus r by a naught, and for the normalization you have 1 by square root of a naught to the power q. So this, I think, you should remember. This will come very often in the course. Okay, so moving on. Okay, this should be easy for everyone. So what is the quantum mechanical operator for the momentum of a particle moving in one dimension?
It's option A.
Option A. Everyone agrees with it, or anyone has any other opinion? So option A. So if you apply this operator on a quantum, on a state, it should give you the momentum of the particle. Okay, so yeah, this is the momentum operator. Okay, let's move on. So Okay, so yeah, this question is about the probability current density. So this is a term you should be familiar with if you have taken a quantum mechanics course. So it's like so you have in the electromagnetic electromagnetism you have a current density sort of when charges flow, you can define a J called current density. Similarly, similar to that, you can define a probability current density for a particle, uh, which means which is a function of both space and time. So uh, it has a very nice interpretation, uh, and its expression is given by this formula. So we have to calculate the probability current density for this quantum for this wave function. Okay, so let us apply this. Okay, so first we need to find the conjugate wave function, so psi star. So it will be simply this, right? And then we will apply here. So psi star, and then del psi by del x will be uh, ik, no, sorry, you should also do on your own this exercise if you want. And then here psi k. Also let me know if I do some mistakes. Mm, okay, so no, one thing you should notice here that uh, is this normalized? I mean, is this wave function normalized? That is, if you calculate this, it should be 1, right? It's not the case. So because yeah, this psi star, and then you can take out ik common, you will get minus 2 kx again we can take out ik common. So I'll write this one first. Mm, okay. I think we'll have to do one more step. So I'll just do this multiplication psi star into this, and let's see what happens. So ik and then this into this, just one, this into this is 2ikx, then this into this is minus 2, and then this into this is 4, right? Am I doing it correctly? Plus 4, then minus 1, then minus 2, right? Okay, now let's see what everything should cancel out, right? So ik, let's take ik common, and we have 1 plus minus 2ik x minus 4 up to minus 4, okay, minus plus 1 minus 2 minus minus plus 2 kx, right? So this, sorry, ik is not here. This cancels out with sorry, this is plus. This cancel out with this cancel out with this, and we are left with, so I'll write here I get cancelled, okay, and we have 2 minus 8. Have I done any mistakes? 1 plus 2
So maybe the signs of the force should be different, so that's how we can cancel out the force.
Oh, wait. Sorry. Yeah, what did you say?
So the signs of the force must be different. So that
That is also what I am thinking. But here we have minus and here we have plus. So this would be minus, right? And then here we have plus and plus. Oh, okay. Sorry, yeah. This, yeah, this will also be minus, right?
yeah, so then minus into minus will become plus, so those both will get cancelled.
Mm, let me see. Uh, just a second. I have to attend a call. So, yeah, what you were saying. Uh, yeah, I have messed up somewhere the minus sign. So, okay, let's assume that uh, 4 get cancelled. Yeah, it should get cancelled. So then we will have just the 2 here, and then 2 is also getting cancelled, so we'll have k by m. So this is the probability current density. It should be constant. I mean, it came out to be constant. So what does it mean if this is constant? Has anyone any insight? What if it were not constant? It came out to be function of x, or I mean, yeah. So then what would we say?
So does this mean that the particle is contained in a particular space?
No, that is not true, because it I don't know, for a free particle, if you calculate it, it should also be constant. You can try, but this is a wave function of a free particle, right? Sorry, this is a wave function of a free particle. I mean, not exactly, but so it is not true that it is confined. So it is constant. That means that, so remember the probability current density, right? It's the current regarding the probability of, so 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 basically the probability of finding this particle, okay, uh, at a particular uh, point, this is given by this wave function, right? I mean a square, psi square. This is the this is what we say, the probability of finding a particle at any point x.
And so here j of x comma t is also the it is used for finding the probability of the particle being in
No,
that
no,
place.
no. That's what I'm saying. This is so this is different. Okay. So the probability current density has has another explanation. So, mm, which I which I sort seem to forget right now. Let me remind myself. Mm. So it's I think it's related to. It has very nice experience. So I mean, you should all go and read about it. Okay, I'll also go and read about it. It's a very nice concept. And why does and why should it be constant? Okay, and in which case this will not be constant. So this is very interesting. Okay,
So, sir, here J, the function J is what? Is defining what?
J is yeah. This is just just an expression. I'm asking what is the interpretation of this equation? The probability current density. What does it mean? It has a physical explanation. It being constant means something. Okay, so that's what I wanted to know, and that's what I will look for it. You should also go and look for it. Okay. Okay, so maybe it's related to maybe it's related to mm, I don't know. I cannot recall. I'll have to look for it. Okay. Okay. Let's discuss it next time.
Sir, does it
Hmm.
mean the opposite? Like the particle can be found anywhere in the surrounding. It's not confined, but it's the possibility of finding it anywhere is it's there. That such a possibility is existing. Matlab the particle is anywhere in the entire observation area. Does that is that what it means?
Mm, any no, I mean, so you see, there is no time component in this wave equation, wave function, right? It's the spatial component. I mean, uh, so it's this wave function is there, okay, and then what are you saying is, I mean, I don't know. I cannot understand what you want to say, but that is not the case. It is something else. You just pick up Griffiths or any book. It's there. You can read about it. Okay, and maybe if you guys interested, I can discuss next time. I'll also have to read. Okay. Okay. So let's move on right now. Mm. So the next question is about the parity operator. So do you know about this parity operator? So let me just write it. So parity operator in quantum mechanics does this with a wave function. Okay, it changes the coordinate. I mean, it's just put a negative sign on all the coordinates. Change the parity. Then which of the following statement is not true? So Any guesses?
So what is that cross symbol, sir, for the
Oh,
superscript that?
this is hermiticity. I think.
I think option D is not.
Option D.
Yeah, that's what I think.
Okay, someone has picked option D. Anyone has any other opinion? Hmm. Okay, so I think you are wrong.
Should it be option B, sir?
Option B. Okay, let's we can do it, right. We can apply on p square on this. So what will happen? So applying p on this gave us this. So applying p square on this means p on this, and you know that the parity changes the sign of the coordinate, so it will give you just again this x. So p square basically means applying identity, right? So this one is not uh, true. This one is true basically, right? This is the feature of parity operator. So then this must be not true, right? So this is the correct option, right? And you guys should go and check whether this and this option is how these uh, are, you know, true for the parity operator. So this is the hermiticity, and this is the unitarity of the parity operator. So yeah, this should be simple proofs. So this you should also go and check, okay, for the parity operator. Okay.
I had a doubt regarding the previous question.
Yeah.
Yeah, actually, if psi is an odd function,
Mm-hmm.
then option A is true.
Option A.
Yeah,
No,
that's what
I
I
mean,
think.
see, we are not specifying whether psi is an odd or even function. I mean, uh, that will come later. Okay, we are just operating parity on a given wave function, and that has the property to just change the. So whether the psi is an even or odd function. So let's take cos x. Okay.
Yeah,
So if you apply parity on cos x, it will give you cos minus x. Okay. Now it is, then the odd and even thing will manifest after this. So here you can write again cos x, right? But we are just applying parity operator. We are concerned till here. We are not going into the details of what this wave function is. That will be a particular case.
okay.
Okay.
Thanks.
Yeah. Okay. So let's move on to the next problem. Okay. Now we are getting into nuclear physics. So yeah, this is a simple problem if you know the radius of the nucleus formula. So the radius of copper nucleus is given, and we want to know the radius of the magnesium. Mg is magnesium, right? Yeah, magnesium nucleus. So how do you do that? Anyone has any idea?
So the radius formula
Yeah, what is the formula of the radius?
R naught into a power 1 by
1 by
3.
3. What is R naught? It has some value, right?
So I guess 1.3.
1.2, I think. 1.2 for,
1.25 for me.
yeah, 1.25 to be exact. Okay. So, but we don't need it because it will get cancelled. So, for copper, we have so radius of copper R naught, and copper has A equal to 64, and radius of magnesium will be R naught, its A is 27. So we can just divide these. So Rmg by R copper equal to R naught get cancelled, 27 by 64, 1 by 3. Can we reduce this? Is this correct? Oh, sorry, it's 63. No, sorry, it's not correct. Yeah, how can we reduce this? 14, does 14 divides 64? Divides, right? No. Mhm. Mm, I don't know, but yeah, you can do the calculation.
I don't think so. You can reduce just directly calculator.
Yeah, you can use the calculator and you have everything. So yeah, just let's not waste the time. You can calculate it. But can you guess what could it be? So for
Option D,
option D,
3.6.
mm, yeah, should be close. Yeah, I don't know. If you're saying, I'll take your word for it. Okay, then next problem. So all of you are able to follow, right? If anyone has any doubt, you can ask. No, no need to get shy and hesitant. Okay. Okay, so here is a nuclear reaction. again a problem from class 12th maybe. So you have a carbon atom, carbon nucleus, and we stuck it with a neutrino. What happens is we get a nitrogen nucleus plus something. So we have to know what this something is. So anyone has any idea what this could be? First of all, is this possible? Is this thing possible?
So if the neutrino decays in one of the protons, maybe yes.
A neutrino decays into proton. How can neutrino decay into proton? It violates everything.
Because there's a contribution to the number of protons, right?
Yeah. Yeah, proton is increasing. So you are saying neutrino or neutron?
No, sir. I meant to say that the number of protons is increasing because there's a contribution to that. So one of this thing must have converted into the
Yeah, yeah.
proton.
So which could have converted? Like
Not sure, sir.
neutrino cannot go into a proton, right? Neutrino is
Yes, sir, yes, sir.
a very different thing. Neutron can go, right?
Yes, sir.
Sorry. This thing is possible, right?
So from this we get one electron outside, right?
Yeah. But let's, I mean, but do you agree this thing is possible? Like so neutron in this one of the neutron in this 13 will go to a proton plus electron, right?
Yeah, but on the right we still have 13 neutrons.
No, this 13 is the total number of neutron plus proton, right?
Yeah, yes.
So this is the A, is the
Yes,
atomic
right.
number. Yeah. So we get a proton here, and this X would be an electron. So neutrino can never decay into a proton or any hadron. It's a lepton, right? So lepton cannot decay into a proton. I mean, in a hadron. I mean, it can in some rare high energy case, so, but not here. Yeah. So, for example, in an electron positron collision, we get uh, we can get a proton. Or no, not a proton, maybe a pion, maybe a meson. Do you know how it can happen? I mean, it's a very advanced thing. I mean, it happens in collider physics. So if you smash two electrons and positron with very high energy, it will just give rise to a quark antiquark pair, and that can form a pion or something else. But yeah, this is a different thing. This is just a simple nuclear reaction. Here these things cannot happen. So neutrino cannot ever decay into proton or neutron. Okay, just keep in mind. Okay, so the correct answer is electron. Okay, so let's go to next problem. Okay, again a boring question. So what is the estimated radius of, what is this, Ni? I don't know what is this.
Maybe nickel.
Nickel.
Nickel it is.
Okay. Yeah, so what is the radius? So again you have this formula, right?
5 fermions.
And
D.
you know the 64 how much?
D.
Yeah, D. Okay. Yeah, because you will get 4 here. 4 into 1.5 is 5. Okay, nice. 5 Fermi. 5 Fermi. Hmm. It's a very small number, right? And so by the way, so is this formula give you the exact radius of the nucleus? I mean, how much did you guys ever wondered how much this estimate could be wrong? Like pick up a nucleus, xenon. Do you know about xenon? So xenon is not a spherical in shape. I mean, it is more like, it's a deformed nucleus. It's like a almond shape something. So here this formula will not be very accurate because you have elliptic kind of geometry here. But yeah, this formula is yeah, first order estimate. For the first order estimate, this formula works fine, so we just run with it. But you have to keep in mind that the exact shape of the nucleus is very different, and you cannot really know the exact radius. I mean, you need more sophisticated techniques to do that. Okay. So yeah, let's go to the next problem. So given A, you have to find the Z value of the most stable configuration. So sort of for a given A, you can have multiple number of atom nucleus. So for example, here you can have carbon, you can have neutron, sorry, nitrogen, you can have other nucleus. But which will be the most stable? How do you find? There is a formula, right? You differentiate the semi-empirical formula and put it to zero, and then you get the expression for the value of z. So what is that formula? If anyone remember?
It's the semi-empirical formula for binding energy.
Yeah. But for the most stable configuration, you have to differentiate it as a function of a, right? As a function of j. No, as a function of a. Yeah. And then you get a formula. So I have written it. It is this. I don't know if this was taught in the lectures or not. I don't know. Is this one discussed?
I don't think it was there in the lectures.
Okay, yeah. So it's just you have the binding energy formula AV, whatever this formula is there, right? The semi-empirical formula.
Yes, sir, this is there.
Yeah, you just differentiate it as a function of a, okay, and put it to zero, and then you will get this z equal to this formula. Okay, so you have the bind. So this thing you can plot as a function of, oh sorry, the function of area. So it comes like this. So you want to find this point where, uh, sorry, not as a function of a, function of, function of z, right? Oh, for each a you have a graph like this. So this differentiation should be also as a function of z, not a. Okay, so here you get the minimum, minimum binding energy. So this is the most stable configuration.
So, but stable configurations require higher binding energy values, right?
Mm, mm, uh, higher binding energy, does higher binding energy, yeah, is that so?
Yes, sir. So, the calculated nucleus ka mass minus the binding energy, the mass due to the binding energy. So that
Yeah.
difference needs to be reduced as much as possible. So, binding energy needs to be more.
Yeah, you are right. But what I can recall, the curve is something like this, and then you have a minima here. So yeah, I'll have to go and check, and maybe you can also check. So
I think the binding energy per nucleon should be maximum, but the overall binding energy should be minimum. But
mm,
it's my opinion.
But if binding energy per nucleon is maximum, then the net binding energy will also be more ordinary, right?
no, yeah, it shouldn't matter. Maybe
Yeah,
this
that makes
curve is for
sense.
binding energy per nucleon, or
So I think the functions need to be different. Uh,
yeah. No, but I clearly remember that this should be the curve should be like this, and then here you find the minima, which is the most stable configuration. But yeah, I'll just yeah, here is I mean there is some confusion what you are saying. So yeah, let's go and check this one also. Okay.
Sir, should the BE be in the X
No, no,
axis?
no.
No, Y axis. No.
Yeah. Yeah, I have also not gone through it all. So I'll go through it and let's discuss again next time. Okay. Okay. So one last problem I think for today. So it's a calculative problem. So the mass of what is this sulfur is given. Mass of sulfur is in terms of atomic mass unit U, what is called I don't U, and 1 U is equal to 931.5 MeV. So we can convert it into MeV basically, and then mass of proton and neutron is also given. Mass of neutron 939.56. So neutron is little heavier than proton, and we have to find the binding energy. Its binding energy. So binding energy is what? So this is the mass, and these are the individual mass of the constituents. So binding energy will be the difference of this mass. So mass of sulfur minus, so how many protons are there? 16 mp plus 16 mn. So this you calculate will be the binding energy, right?
Yes, sir.
Okay. So yeah, this is a very simple problem. What is the time? Okay, I think oh, someone has calculated it. Okay, it's fine. 279.34 MeV. Thank you. I don't know if it's correct, but I think yeah, it should be close. It should be. It is very low. I don't know. In terms of, yeah, it should be something like this. Okay. Yeah, this was the last question. So yeah, so yeah, these are recorded also, and if you missed anything, you can check again, uh, going back, and the slides will also be uploaded. And yeah, sorry, I was not at all prepared for today's session, so sorry I was not able to answer many of the questions, but I will come prepared next time, and we'll have a good discussion. Okay. Uh, and yeah, some things that we missed today, we will have a discussion in the next session. And if we have some time, so can we all have a introduction of ourselves? So first, I'll go. So yeah, I mentioned my name is Rohit Kumar Singh, and I'm doing PhD in the field of experimental high energy physics. And so I work in the area of heavy ion collisions. So where we smash two heavy nucleus like lead and gold, and we then try to study the properties of the matter which get formed. It's called quark-gluon plasma. When we smash two nucleus at speed of light, so this smashing is done at the Large Hadron Collider in CERN. If you all know what CERN is, a very large collaboration of uh, experiments, and one of the experiment there is CMS, which I am involved with, and there we study, there we take data of these collisions, these nucleus collisions, high energy at high energy, and then we try to understand the properties of quark-gluon plasma. So that is what I do. I don't do much nuclear and particle physics. Uh, so my area of research is very different from this course. But yeah, I mean, these are basic things, so we all must know these things. So okay, then we can go one by one. Also, do you want to ask anything about myself, or maybe we can go to who is this one two? Why you are numbered, not name? Hi, one two. Who is this? You can unmute and just give a quick introduction, like uh, what are you studying, and where are you from, which institute are you from, just to get an idea. uh, I think he cannot listen us, so let's go to Adnan.
Yes, sir.
Yeah, also you can if you want, you can turn on your video, so we all can see you.
So my webcam is not connected right now, so
Okay, okay, no
I
problem.
mean, excuse for that.
Okay, yeah, just yeah, tell us about yourself.
So my name is Adnan Pathan. I'm a third year in aerospace engineering student. I'm studying in Dayanand Sagar University, Bangalore.
Okay, so you are an aerospace engineering student.
Yes, sir.
So why did you take up this course? Like, you are interested in physics, or?
Yes, sir. I'm interested in physics. I want to pursue research in physics and theoretical physics and those in the future. So that's why I
Okay,
thought I should like familiarize myself with these subtopics of physics.
okay, that's nice. Okay, thank you. All the best. So then we can go to Avni. Avni cannot speak, so she has dropped a message. I'm a BSc first year student. My subjects are physics and maths. Okay, thank you. Uh, then we can go to Deepika.
Hello, sir.
Hi.
I am Deepika. I'm doing masters in physics.
Okay, masters. Okay,
Sir, I'm interested in theoretical and nuclear physics, so I thought of pursuing this course.
okay, that's nice. Thank you.
Thank you, sir.
And then we can go to Jyotsika.
Yes, I'm Jyotishko and I am from Kolkata. I am studying in Indian Association for the Cultivation of Science and I'm doing the 5-year BSMS course. And
Okay,
I'm currently in the second year. So I
okay,
haven't
nice.
got my major yet, but I want to pursue physics, especially astrophysics, if I could.
Astroparticle physics or astrophysics?
I haven't specialized thinking. I'm not thinking about specializing it, but
Okay,
yeah,
yeah, but you want to, go into the astro part of the physics.
yeah.
Okay, okay, that's nice. Then we have Sarda. No response. Okay, no problem. Maybe next time. Okay, so thank you guys for your kind introduction and interaction. So, yeah, let's end the session for today and we'll meet next Saturday, same time. So, I hope to see you. Okay, one, two has replied. So, hello, sir. I am Ayush from West Bengal. I'll be starting my third year in the Department of Physics at ISER Kolkata from August. Okay. So, okay, thank you. Uh, thank you, Ayush. So, okay, thank you all. See you next week. Bye.
Thank you so much.
Bye.